the first of several short videos in Chapter 6. We saw at the end of Chapter 4 that if we had uniform circular motion with an object moving around in a circle at constant speed, that even though its speed was constant and it had no change in velocity in that sense, it could still change velocity in terms of direction. And because it changed velocity as a vector in direction, that means it still had an acceleration associated with it. In this case, the centripetal acceleration. So we want to reinvestigate that. Let's say we had a mass moving around in a circle, some velocity v. So there's going to be a centripetal acceleration associated with its change in direction as it's moving around the circle. But we now know that if there's a mass and an acceleration, then there must be a net force. So associated with this mass and the centripetal acceleration is a centripetal force. So by Newton's second law, mass times acceleration is our centripetal force. Now this is a net force, so there could be many other external forces that are responsible, adding up positive or negative, that ultimately give us this net force towards the center of this circle. And so the centripetal force itself is not a physical force, it is the net force of all these other external forces adding up to give us this net force. But it is the mass times the centripetal acceleration, mass times v squared over r. Here's an example. A ball of mass 0.5 kilograms is attached to the end of a cord whose length is 1.5 meters. The ball is whirled in a horizontal circle. If the cord can withstand a maximum tension of 50 newtons, what is the maximum speed the ball can have before the cord breaks? This might be similar to the problem encountered by David when he was trying to slay Goliath, as he's whirling a ball around in a circle. And in this particular case, the cord is going to break. And when that does, we will go from having an acceleration and a centripetal force to no acceleration. And Newton's first law would then take over, and the ball will continue to move in straight line motion at constant velocity from that point. David is whirling this around, and at some point he wants to release the projectile, and then it will go in a straight line motion from that point on. So in this case, we have a centripetal force, we have a net force, and it is being supplied by one external force, and that is the tension in the cord. Once that tension is released, then there's no net force, moves according to Newton's first law, straight line motion. So we have mass times acceleration is our net force tension. We want to solve this for our maximum speed at the maximum tension. So multiply both sides by r, divide by mass, take the square root. Our maximum velocity will be equal to our maximum tension times r, divide by the mass, square root. 50 newtons times 1.5 meters, divide by 0.5 kilograms, square root. 12.2 meters per second, which would be about 27 miles per hour. So if you fling this thing around at 27 miles per hour, then that would give it too much required to try to hold it in a circle. The cord will break, and then it will go flying off. Let's try another example. A 1,500 kilogram car moving on a flat horizontal road negotiates a curve whose radius is 35 meters. If the coefficient of stack friction between the tires and the dry pavement is 0.5, find the maximum speed the car can have in order to make this turn successfully. So we're going to say that stack friction is responsible for the centripetal force in this case. Why static friction? I mean, the car is moving. Why is it static friction? Well, because the car is moving in a forward direction, but we're talking about a acceleration towards the center of this circle, a force towards the center of this circle, which is perpendicular to the direction that the car is actually moving. So the motion of the car is in one direction, tangential on this circle, and then the radial force is going to be towards the center of the circle, and there's going to be hopefully no movement of the car in that direction. It's going to maintain the same radius that's going around the curve. So that actually will be a static motion in the radial direction. Hopefully it's not going to slide out and then becomes kinetic in the radial direction. So it is static friction on the side of the tires that is holding this car in its circular motion. So we have our net force is mass times velocity squared over r, and that is equal to whatever external forces are responsible for keeping this moving in a circle. In this case, is strictly static friction. It's going to be mu times the normal force, but in this case the normal force on a flat plane is going to be equal to the weight, mg. So it's going to be mu times mg. In other words, our frictional force is going to be 50% of our normal force, 50% of our weight, because mu is 0.5. Okay, in this equation, mass is going to cancel out, and we're going to solve this for the velocity that we can achieve. Multiply both sides by r, take the square root. So our velocity will be equal to mu, which is 0.5, no units associated with that, g 9.8, r was 35 meters, square root. We can go up to 13.1 meters per second when we reach our maximum possible static frictional force. So that would be very close to around 30 miles per hour. If you were a civil engineer, then you would design or at least put up signs saying you can't go faster than 30 miles per hour on this curve in dry conditions. On a wet day, though, the car described in this example begins to skid on the curve when its speed reaches 8 meters per second. What is the coefficient of static friction in this case? In other words, when the road is wet, the static friction is going to change. So we still have our centripetal force supplied by static friction, only in this case our mu is going to be smaller, and we want to solve for that. Get rid of the mass on both sides, divide by g, so we can solve for mu. So mu is going to be equal to velocity squared divided by g divided by r. That's going to be 8 meters per second squared divided by 9.8 divided by 35 meters, 0.187, no units on it, and hence, because it's wet, the friction has been reduced to only 18.7% of our weight rather than 50%, and hence we can't go as fast on that curve in order to negotiate the curve safely before we start to slide outward. So, something to think about, something to consider if you are a civil engineer. Let's try another example. Let's go loop to loop. Find the apparent weight of the pilot in this loop to loop, a vertical loop, at the bottom, top, and side of this vertical loop. Let's say we're going to consider the pilot at the bottom of this loop, and it appears Einstein is the pilot. It's a little known fact that Einstein was a great fighter pilot. In fact, I didn't even know that either. In fact, I don't think anybody knows that. So, definitely a little known fact. But if we did a free body diagram of Einstein, the pilot, we would notice that there was a force, a normal force of the seat on him, pushing upward. Of course, he's got weight, mg, pulling down towards the center of the earth. And since he's at the bottom of this loop, the acceleration, the centripetal acceleration, would be towards the center of the circle, which is going to be in an upward direction at that point. So our centripetal acceleration is upward, our radial acceleration is upward. There is no acceleration in the forward direction because he's moving at constant speed. And so there is no tangential acceleration in this particular case. So this constitutes our free body diagram for the pilot. a normal force going up, gravity going down, and an acceleration going up. We use this to set up our Newton's second law equation. In this case, the acceleration direction is our positive direction. So we would say that our net force, which is mass times acceleration, is equal to the net force in the direction of acceleration, which in this case would be the normal force minus mg. So the normal force of the seat at the bottom of this loop minus mg. We can use this to solve for the normal force of the seat. And that is equal to mass times velocity squared over r plus mg. What does this mean? If you were this pilot going loop to loop, at the bottom of this loop, you're going to be sinking into the seat, and the seat's going to be pushing back. And the force that it pushes back with, the normal force, is going to be equal to at least your weight, mg, plus an additional term, mass times v squared over r. So, since that is reaction force, and you're pushing in and it's pushing back, and those, according to Newton's third law, those are equal and opposite forces, you're going to appear like you weigh more than what you actually weigh. So you're going to feel like you're sinking in the seat. You're going to feel like you weigh more than mg. And the amount you weigh more by is this mass times velocity squared over r. How about that? What happens if you're at the top of this loop? Let's do a free body diagram of the pilot at the top. Well, you still have weight headed down towards the center of the earth. In this case, the seat, the normal force of the surface of the seat, is also headed down as well. And you're at the top of this circle, and the acceleration, the centripetal acceleration, is towards the center of the circle, so that is also down. So there's our free body diagram for the pilot at the top of this loop. We set up Newton's second law for this free body diagram, and we'd say our net force, mass times acceleration, is equal to the summation of all the forces in the direction of acceleration. And we have two positive forces in the direction of acceleration being our positive direction. So we have the normal force of the seat at the top plus mg. Solving for this normal force, we now have that is equal to mass times velocity squared over r minus mg. And that is the force of the seat on us. Now we can see that if we're moving fast enough at some radius of this circle, that it's possible that this first term will be equal to our weight. And at such a point, we actually will leave the seat and not really even touch the seat. The seat won't have any force on us, and we'll feel at that moment like we're weightless. How about that? In other words, gravity would just be enough to supply the centripetal force, nothing more, nothing less. We won't fall, but we won't move outward either, and we'll feel like we're momentarily weightless. NASA employs this technique in what is called, in the airplane that they call the KC-135. The KC-135 is a reinforced plane. It's a regular plane, but it's got these extra metal and rivets on the side to allow it to take extra stress. And it goes through these parabolas. And as it's going up through the top of a parabola for about 20 seconds, it achieves basically zero gravity, or, well, the semblance of zero gravity. Your gravity is actually maintaining you in that circular motion, nothing more, nothing less. So if you were inside the cabin of this plane, you would be flying around like you were zero gravity for these 20 seconds as it's going through this parabola. And you would, for all practical purposes, believe that you were weightless. I mean, you were basically falling. So if you were conducting an experiment that will someday go into space, you might test it out in the KC-135, and for 20 seconds at a time, you would have weightlessness. So you might have an experiment, maybe you're trying to melt something and see how it melts in space. So you have a furnace there, and you're there inside the plane, and when you hit weightlessness, You push the button, run your experiment for 20 seconds, push the button to stop it, and then you wait for the next parabola so you can push the button again and continue running your experiment. So you run it for 20 seconds at a time. Seems like a lot of trouble, but to put an experiment out in space is billions of dollars. So you can run it on this PHY213 and test it out for a lot less money, and then before you decide to actually put it up in space. So it's a good idea. Being somebody who used to work in the Space Science Lab at NASA, I used to work on experiments that would go up into space, and I had the opportunity, I was given the opportunity to go on the KC-135, and I turned it down because I knew that with my constitution I would not survive more than one parabola. I would lose my lunch somewhere along the way very soon. And the KC-135 does not just do one parabola, it does 40 parabolas before it stops. So they will not stop the plane for you if you get sick. So you have to endure 40 of these parabolas. Zero gravity at the top, and then when you hit the bottom, you endure up to about 3 Gs. So you feel like you weigh 3 times as much at the bottom of the parabola. So 3 times as much, 0, 3 times as much, 0. And it makes me sick just thinking about it. 40 of those before it stops. And not to mention the fact that you're in a plane, being an engineer type, that this plane is going through incredible stress. It's going through this. So if you don't like flying in planes, you don't like to fly in a plane that is going through that much stress all the time. So leave it up to the true astronauts. But that's something that you can do to save money. You get the same effect on a roller coaster. If you go on a roller coaster, you go to the top of the hill. You feel for a moment like you're weightless. You actually fly off your seat for a bit and kind of fly for a bit, and then you go down to the bottom of the roller coaster and you're stuck in your seat because you got a lot more weight. And actually, if I go on a roller coaster, I like going on the roller coasters that actually go faster, because then you feel like you're stuck in your seat a little bit more and you feel a little bit safer on those roller coasters. If the pilot were at the side of this loop-de-loop, the free body diagram would look like this. You have a normal force of the seat towards the right in this case. Weight is still going down. In this case, all your normal force is supplying the centripetal force that's keeping you in the circle. So if we wrote Newton's second law for that, mass times acceleration would just be equal to your normal force at that case, and that's what the force of the seat would be on you. That concludes our very short lecture on centripetal force, and we will have another short lecture next on fictitious forces.